Maybe I'll give you extra credit. Maybe I give extra credit if you come with a costume.
I will come got it. I will come exercising unit.
Yeah. Come, do.
17th century clothing.
Exactly. Okay, let's start the class. And okay, we were talking about Newton. This is Newton's first law, right? So inertia in physics is the resistance to change the velocity. So more inertia, more laziness. Inertia is just the mass, and the unit is in kilogram. So don't confuse the weight. Weight is a force. And there is a question on that for test number 2. The weight is a force is the mass times 10 or mass times gravity, right? It's not the same thing as the mass. The mass is in kilogram. So if you are on the moon or in space, this anvil here will have the same inertia. So it doesn't matter if you are on Earth or in space, it's going to be as hard to push. Of course, if you are on the moon and you try to lift it, it's going to be easier because it doesn't have the same weight. Okay, so we talk about inertia. Something like this also maybe on test 2. You see, because of inertia, when there is no force acting on the system, it will keep moving at the same speed along a straight line. Okay, so we talk about that. That's okay. So here the acceleration is inversely proportional to the mass for the same force applied, but it's proportional to the force for the same mass. Okay, we talk about that. So if you have, for example, a child who has a small inertia, adult that has a large inertia, and you want them to get to the same speed, obviously, they're going to stay in the plane, right? They're going to reach the same speed. So they will both have the same acceleration. But because they don't have the same mass, more force will be applied to the adult than on the child. So that's why in the airplane, you can see the kids, they sit, on their chair when the airplane is taking off and they don't need to, you don't feel crushed. Heavier you are, more force you're gonna feel, and more crushed you are on the seat. Right? Does it make sense? Okay. So Newton's third law is something that is not intuitive. Also on test 2. For every action, you have an opposite and equal reaction, which means you cannot push harder than you are being pushed, and you cannot be you cannot push harder than and you cannot be pushed harder than you are pushing, which means if you hit the wall, right, with 5 pounds, and the wall cannot defend itself, obviously, but I'm going to be punched with 5 pounds. You know that, right? If you do boxing, you punch a bag, it's going to be punching back, right? So the force is always the same, not the consequence. So what do I mean by that? Let's say you are in space. So this is very heavy. Maybe it's some kind of spacecraft and you have an astronaut and he's pushing the spacecraft. The force will be the same. You push, it's going to push back on you. For every action, you have an equal and opposite reaction. So the push is the same, but not the consequence. F equals ma. So the same push applied to the spacecraft, because force equals mass times acceleration, it has such a large inertia that it's going to hardly bulge. Like it's so tiny that it's not going to move. So everything goes to the mass. Is that clear? The same push will be applied to the astronaut, but because his mass is small, right? He will be going through a larger acceleration. So small mass, large acceleration, large mass, small acceleration, but the force is always the same, which is not intuitive at all. It's good. You have to break. I worry now. You scare me. So every push, you have a counter push. So example, I am about, very sadly, I don't know why I keep gaining weight, make me very sad. But if I am 170 pounds, that means the earth is pulling me with a force of 170 pounds. If you want to know in Newton, you divide by 5. So the earth is pulling me with 170 pounds. What is it I am doing to the earth? I'm pulling back with 170 pounds. I'm pulling the earth. You have this power, right? If you are 150 pounds, good for you. You're going to pull the earth up with 150 pounds. But of course, the earth doesn't move because it has a huge mass. So if I was to step on the desk and then step like falling, I'm falling toward the earth. The earth is also falling toward me, but you won't see it because of inertia. Okay, so for every action there is a reaction. We call that the Newton pair. And it's not that intuitive. So how can we explain the lift, for example? It's because we have an atmosphere. So you push on the air, so the air will accelerate down. Okay, you see, you are pushing on the air is deflected down. So the air is going to push back. Which one is accelerating? So here there is a balance. So this is called the lift, right? So how do we explain the lift? You push on the air is pushing back on you. We don't care about the air. The system we are considering here is just this air, it's not a wings, I don't know what it's called. Planner. It's a planner, right? So you see it's acted upon by two forces, lift and weight. And if it's in equilibrium, doesn't go up, doesn't go down, that means the two forces equal to each other. Up equals down, right? So here it's not intuitive. It doesn't matter if you have a very strong man and a weak man. The force is always the same. If this guy wins the tug of war, it's going to move. You're going to have an acceleration, but the force is always the same. So I don't know if I can show you that. I have two spring scale here, and the outside is in pound. I don't know. It's you use that to measure the weight of the what? Like the bags and luggage? Yeah, the luggage, exactly, the luggage. You can cheat with the luggage, right? When you have them on, when they weigh them, you put your foot and you lift a tiny bit. Because you think you buy a cheap ticket and then they charge you so much. I need a volunteer to be strong. Wants to be strong. Let's strong. Okay, come. You will be strong. Try one. That's different. And you're gonna read here, right? And you will give a witness that the reading will be the same. You can do that for demo, right? For example. So we are both really we are as strong, right? You read the same thing? But now she's very strong. Pull me. Pull me. Move. Do you still read? You're gonna still read exactly the same thing. And now I'm gonna pull you. Quite someone strong. Do you see? It's gonna be the same reading. Thank you. So, what's your name? Carol. Cara. Carol. Cara. Yeah. Come on, I have my first name is Veronique. Who can pronounce it? Right, Veronique. It's hard, no? So the force is always the same, but not the consequence. So, for example, what is that? It's someone's phone. Okay, I'm gonna give you another idea for demo if you need extra credit. You'll decide after the test if you need. Okay, so that's a student of mine long time ago, and she did that demo with her dad, who is obviously stronger than her. So she took two bathroom scale and she taped them together, right? So first they did like we did. I push the same amount and you see the same force. But after the dad is overcoming, right, because he's stronger, so it's going to move back. But the reading on the bathroom scale will be the same. Before starting, you have to calibrate, right? You want to make sure it's 0 on both sides.
Hi, my name is Angelica, and I'm in Physics 105. Today, me and my dad are going to be doing the scale.
So she taped the bathroom scale together.
As you can see, they're aligned. As you can see, the scales are aligned. But I'm going to set it to 0. That way both of the scales read 0. So we're going to push.
So the reading will be the
It's
same
about equal.
on both sides, about,
Mine says
right?
20,
70 pounds.
Okay. And then
Of course,
now,
it's going to wobble a little
he's gonna
bit,
push
but now
even
he's
harder.
pushing
Oh my God,
harder, very hard, and you still have the same reading.
okay.
So the consequence
it.
is not
Thank
she's
you
going to be
for
pushed
helping
back,
me.
but the force is always the same. So if I try to trick you, right, and I say, oh, the force is not the same, the force is always the same, not the consequence. So here is another example. It's called if you play tennis or ping pong or cricket, you have something called the top spin or the back spin. You can make the ball go this way, so it's a top spin, or you can go back spin. So in that case, you have a tennis ball, let's say, and you see it's going to be a back spin. You make the ball goes in this direction. So what's going to happen to the air? The air is deflected down and the ball wants to go forward, but for every action you need to have an opposite equal reaction, so the ball is going to be deflected up. If you play ping pong, for example, here you have a top spin, and what's happening to the air? The air is deflected up, and the air is deflected up. Here, deflected up is going up, so the ball will be deflected down. You can do that with soccer, right? So that will be a side spin. So you make the ball spin in one direction. So you see the air is deflected to the right. So the ball will be deflected to the left. So if you know how to do it, you can make a video. This is called the Magnus force. And I don't know if I have. Okay, here's another idea for a video. It's from the channel
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin.
Backspin.
Whoa, look at that go!
Do you see how it's affected? For every action, you have an opposite and equal reaction.
You want those to get back in the water, do you?
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it and it just took off, like we had no idea that was going to do that.
Okay, and this morning I found this video here. Apparently, I didn't know if you like bowling, you can do the same thing with a bowling ball. You give it a spin, a sideways spin, and then it will be deflected just right to have a strike. It's gonna make it spin.
I saw.
It's gonna be deflected So you can practice if you want. Okay, so here is something not intuitive. You have a truck and a smart. A smart is a small car that it's an Italian car. So go try to park in Italy if you have an SUV. Good luck, especially if you go to Naples. It's already very hard to drive there, but with SUV, forget it. So they have those very, very small cars, and they all drive small cars, by the way. And unfortunately, you have a truck and a smart colliding head front. What is true? The yes, exactly. So it means the force will be the same. They're going to experience the same force, but not the same consequence. That means the change in the state of motion, right? What will happen to the smart is much, much worse. But the force is the same. So it's not intuitive. Same thing here. A little girl playing tug. What is a big guy and a small little girl, little Susie? So what is true? Same force, not the same consequence like with Carla. Carla.
Carolina?
Carolina, Carlota, Carolina. Huh? Carola. Okay, Carola. Oh, Carol. Okay, Carol. And so she was winning the tug of war, right? The force is the same, not the consequence, because I was accelerating, right? Okay, so this is not intuitive. You have something sitting on the desk. The earth pulls the apple down. Okay, so the earth pulls the apple down. What is the reaction? Exactly, the apple pulls the earth. So people want to say the desk. No. It goes in pair. Earth, apple, only them two. The earth pulls the apple pulls the earth. The apple pushes on the desk pushes back, which is called the normal force. So normal force is a reaction force, right? A hammer hit a nail. What's the reaction? Opposite, like switch hammer and nail. So then the nail will push back on the hammer or hit back the hammer will stop it. Okay, so blades of an helicopter pushes the air down, so the air is pushing helicopter up. And this helicopter, they have a special design to make as efficient as you can. Now, why is it that I can walk, but not strong? I can walk, right? Because you push the ground is pushing you back, right? So this is static friction. Static friction is in this direction. That is why I can walk, because I want to slide, and the ground say no. I'm going to push you back. You're not going to slide. So this is static friction, opposing the motion. Okay, so it's not that intuitive. So we used to have this. It's been phased out. Now we rely on Elon Musk. But before that, we had the space shuttle. Terrible accident happened. At least 2 accidents. Challenger and Challenger what? Discovery and Challenger. Challenger was the worst because there was a teacher. It was the first flight with a civilian inside. So it was very sad because you had all the kids, watching the teacher getting into the space shuttle, and all of a sudden, boom, big explosion. So very sad story. So anyway, at the time of the space shuttle, so you need to take boosters here. So those boosters here, the way it works, they don't push on the air. They're gonna burn gas. Okay, you have a fuel. So you have an exhaust gas. So the space shuttle pushes on the exhaust gas. So what is the reaction? Push back up. Consequence is not the same. You're going to have a very small acceleration for the space shuttle. It's like 3g, no more than 3g. So people sitting inside will feel 3 times their weight crushing them, but 3g is not a big deal. So, but the gas will accelerate with a huge acceleration because it has a small mass. So if you want to go in space, you have to bring your own gas to push on it. You have to bring it with you. You have to make it because there is no air to push on. Even on Mars, they have this helicopter. So because Mars has a small atmosphere, it managed to fly because there is enough to push on, and the helicopter is small enough. But you see that was not very efficient because you had to take 20 times the load in fuel. So if you have 5-pound load like a satellite, you need to take 100 times 20, 100 in fuel, so not efficient. And then you will lose the booster because Elon Musk was not around to find a way to bring back the booster on Earth. And Elon Musk, SpaceX has a technique to make it more efficient. Right, so it's going to push on air as high as it can, and then it's going to use fuel. So not a bit efficient, but it was a great time. Everyone wanted to be an astronaut at the time. Here, this is my favorite cartoon. You see, in the movie, he starts to punch, give a jab, right? Punch Baloo. Baloo doesn't do anything, right? But he's still going to be punched back. So you cannot punch without being punched back, and you cannot punch harder than you are being punched. So that's the idea. So here you have something very, very important for what's coming next. The force is the same, not the acceleration. So for the same force, you have a large mass, that balloon, with a small velocity. And what's acceleration is the change in velocity over time. So V final minus V initial, right? So large mass, small change in velocity for the same amount of time. Small mass, large change in velocity. So what I'm going to do here is that you have delta V over delta T. Delta V over delta T. I'm going to multiply both sides by the time, and I get this, right? I have m delta V on one side and m delta V on the other side. This is, my friends, this is conservation of momentum. When two things interact with each other, it's going to be the same force, but not the same change in velocity. But the same force, which means one will gain momentum, the other one will lose momentum. So that physical quantity, so we're going to look at that very soon, mass times the change in velocity, this is called the change in momentum. Momentum was defined for the first time by Newton. He called that the quantity of motion because it's a way to measure how much motion do you have. If you are not going anywhere, if you are at rest, so the quantity is zero. If you have no mass, there is no momentum. Now, I want to bring your attention, especially for test 2. Do remember that velocity is a vector. So when we write down the change in velocity, it's going to be the final velocity minus the initial velocity. This is very important when something is bouncing off. So I'm talking with the test in my head. In my mind, not in my head, in my mind. So let's say something is going like a bouncing ball. Let's say it's 30 meters per second. It's bouncing off. Maybe it's going to lose some energy, but it's still bouncing off here. And now it's 20. So this is the magnitude, but the velocity is a vector. It has a direction. So when we deal with vectors, we need to put axes. So this is positive and this is negative. So final velocity minus initial velocity. It's going to be what? What is the final velocity? Negative 20 minus, and then initial 30. So that's going to be negative 50. For some reason, students have a hard time with that, but remember that the velocity is not a scalar. It's a special physical quantity. It's a mathematical object. It's a vector. It can be negative. It can be positive, right? And sometimes it has components. So you cannot subtract them. If it's bouncing off 30 and then it doesn't lose energy 30, here I'm just writing the magnitude. So the change in velocity will be final is minus 30 minus initial equals minus 60. So do pay attention to that. Now, what do we call, and I will define that later, but the change in momentum. Momentum is a vector. The change in momentum will be the mass times the change in velocity. So I'm going to define that coming soon. I just want to introduce it. So this is called the change. Each time you have a delta, delta means a change, means final minus initial. The change in momentum is the mass times the change in velocity. And for a change in momentum to happen, you need a force. You need to apply a force. Okay? If there is a change in momentum, then there is a force. I had like oh, here is the action reaction. You know, so that's the real thing. Okay, some people they cheat and they have like a little engine here. But if you want to have a crazy workout, but you have to be crazy for that because that's a crazy workout. You do this. Imagine the workout, but the idea is the same. For every action, you have a reaction. So you push the water back, the water is going to push you forward, right? But if you stop, it's going to stop. It's super hard. I don't know if you can do it like as a demo, but it's super hard. Super, super hard. So for every action, you have a reaction. I had another video, but Newton momentum, here you go. If there is a momentum, mass times the change in velocity, then there will be a force applied during a time t. Smaller the time, larger is the force of impact. Larger is the time, smaller is the force of impact. So if there is a change in momentum, you go from something going really fast and all of a sudden stop, you're going to have all that force delivered, right? So here, I don't think they did it on purpose, so I don't want you to do that, of course. We don't want to destroy.
You won't believe what happens at the end.
I don't think that's stupid. I don't think they do it. I hope they didn't do it. So this is perfect to illustrate if there is a momentum, right? And there is a change in momentum. So it's from moving fast and all of a sudden it's going to stop. All that is going to go into a force over time.
You won't believe what happened.
Is that clear? For me, those short, it's gems. I have so many things. Action, reaction. And you see also that the champagne is going to stop. Okay, so change in momentum, and there will be a force, right? But otherwise, it's action, reaction. You push on the gas is pushing back on you. Okay, so that's what we're going to see next. That's a different way to write Newton's second law. A force is applied during a time t, there will be a change in momentum. Or if there is a change in momentum, there is a force over time. So here, if you have bugs on your windshield, is the force the same? Yes, not intuitive. The force is the same, not the consequence, right? The bug is going to end up like this. Huh?
Force change.
Who is in the car? No, it depends. No, it doesn't. It's just change in momentum. Change in momentum. Yeah.
It changes. I'm in the car, and brother's car, the mass changes.
Oh yeah. So it depends on the mass. So actually, if we want to use Newton's second law, so I'm going to apply a force on the bug, and that will be the mass times. So the force times the time elapsed will be the mass times the change in velocity. So larger the mass, larger the force for the same time. Okay. Okay, we already talked about that. Okay, let's go to Newton's second law. Any question? So here you have a website. It's called physicsclassroom.com. And if you don't have the patience to go for a textbook, which I hope you have the patience to go for a textbook, but it's a great website. You have a summary, like it's a summary of everything, and you also have little a few questions. So it's a great website. So so far, so if you so misconception, maybe it's on test 2. Remember, you don't need the force for something to keep moving. Because of inertia, it wants to keep moving at the same speed along a straight line. You only need a force if you want to speed up, to slow down, or to turn. Okay, that will be a centripetal force. But otherwise, if something is moving at a constant speed along a straight line, it means that the net force is 0. All the forces balance out. There is no acceleration. So if you apply a force during a time t, the velocity will change, but it depends on the mass. And what does that mean? Velocity changes. It means you go faster, slower, or you make a turn. Because the velocity is a vector. So you can change the direction. Right? So in his book, this is the most famous book in science. It's called Principia. It was written by Newton. It was not called physics at the time. It was natural science. And he defined his second law as follows. He said, if you apply your force during a time t, time does matter, you're going to have a change. Again, I'm going to write it this way. So apply your force during time t, the velocity is going to change. So it could be you make a turn, you go faster, you go slower. So this is a vector, this is a vector. But of course, it depends on your mass. Right? So if you have a large mass, you're not going to speed up as much for the same force applied. Depends on the mass. So he said, if you have a force applied during a time t, so that will be the time, that's the applied force, right? The net force equals mass, that's the mass, and that will be the change in velocity. So final minus initial. Okay, I'm going to put m for the mass times the final velocity minus the initial velocity. Or you can say apply a force. So we are only working on along the one line, okay? But it's still a vector. So I'm going to still put a vector equals mass times delta V. Okay? So this is called Newton's second law. If you divide by the time on both sides, okay, so I'm going to divide by the time on both sides, and it should be delta t. Okay, so that's the delta t. Okay, so I divide both sides by delta t. Okay, so you can cross this out, and what do we find? F equals m. What is delta v over delta t? Very good. We go back to F equals ma. But this one, you understand more the concept. You apply a force during a time t, the momentum is going to change. This quantity here, it's a new physical quantity, and we call that J, and this is called the impulse. Impulse. The unit is Newton second. This quantity here is called the change in momentum. So the unit will be kilograms meter per second. So this is called the change in momentum. Like the tree that was broken, because there was a change in momentum of the big stone, rock, so it applied a force over time. So this quantity is called the impulse. If there is an impulse, there is a change in momentum. Or if there is a change in momentum, there is an impulse. And this is called the change in momentum. Agree? Now, momentum, we're going to work with that next unit, but momentum is just mass times velocity. So what's a change in momentum? Is just the mass times the final velocity minus the initial velocity. We're going to see that, okay? So what's the change in momentum? Is the mass times the change in velocity. Change in momentum is the mass times the change in velocity. The change in momentum. Okay? That's just Newton's second law. And here we go. The force applied during a time t will cause a momentum to change. So it will cause a change in the velocity. This term here, we call that the change in momentum. This term here is called J, which is called the impulse, and it's a vector. This is a vector, this is a vector. Okay? The change in momentum is also called the change of motion. That's how it was defined by Newton. So let's talk about some conceptual physics here to understand when you are playing tennis. So you are not on something. You don't take anything to what is called steroids. You're not taking that. You cannot be stronger, right? So the force you cannot change. But you want the tennis ball to go as fast as possible. You want to give it as much as momentum as you can. But so you want that momentum to change, right? To be as large as possible. So you make it very hard for your partner to hit back. So you want to increase the momentum, but you cannot change the force. What is it that you can do? So you cannot change the force. So the only thing you want the acceleration, the change in velocity, you want that as large as possible, but you can change the time. This is called follow through. So when you play tennis, I'm sure all of you have played tennis, you don't just go bing. It's not going to go very fast. You, once the ball is on your racket, you follow through. Because when you follow through, you increase the time during which the force is applied. So here, typical conceptual question, you want to follow through, increase the time if the force cannot be changed, and you will increase the momentum, right? So let's do this simple numerical problem. So you follow through, right? Likewise, when you have a glove, what's called baseball, that baseball when you have a glove, right? So you have your glove, you don't just catch the ball, it's gonna hurt. It's gonna hurt, right? You have a change in momentum, you stop the ball. Doesn't matter how you do it, it's gonna be stopped. So the change in momentum does not change, right? It's gonna be stopped. But you want to decrease the force of impact. So what do? You pull back, you increase the time. If you increase the time, you decrease the force of impact. For the same change in momentum, you follow through. So it's not for the same reason. So in that case, the change in momentum is fixed, right? You just stop. You catch the ball and you follow through. Increase the time, remember, for test 2, you decrease the force of impact, yes. Yeah, so the force experience, yes, will be the same. The force is always the same, right? And here you cannot change the force in that case because you cannot increase your muscle. So the only way you can to increase the momentum, you increase the time. But when I say Newton's third law, for every action you have a reaction, when we're going to use Newton's second law, you forget about Newton's third law because you want to focus only on one system. So here we are focusing, it's a good point, you are only focusing on the tennis ball. But yes, they will feel the same force, no matter how you do it. And so let's try to do this one. Let's do the numerical problem. So a lot of applications. Don't forget this also for the test, right? Remember this. Okay, so how it goes. Apply a force during a time t and to a mass, and the velocity is going to change. Final minus initial. That's Newton's second law. So what do we have? We have the mass. This is the mass. The speed. So this is the initial speed. No, it's not no. When you begin, what's the speed? 0, right? You start from 0. So that will be the final speed. The initial speed is 0. That will be the final speed. And that will be the time of impact. Okay, so force times the time of impact. It's milli. So milli is 10 to the negative 3. Right? You substitute milli by 10 to the negative 3 equals 0.06 times the final is 40 minus initial is 0. 480. Did you all get 480? Okay, so be careful when you do the computation. You want to make sure you frame the denominator. So here, open the parentheses. And the in Newton. And this is actually the average force. Any question? So you need to have a good follow through because you increase the time of impact for the same force. So the speed will increase and it will have more momentum, also more force. So usually in the equation here, you cannot apply the same force. So that equation will have like an average force. It's the average, but we won't worry about it. But it's really the average. Now you have a textbook, right? Johnson and Cotnell. You really have to go through the solve problem. Open your textbook. So this is called the impulse momentum theorem or Newton's second law, right? So here you have the net force times the time of impact equals mass times the change in velocity. Okay, force times time equals change in momentum. So this is called the change in momentum. This is called the impulse. Agree? So for the same change in momentum, you can apply a large force during a small time, or you can apply a small force over a large time. So this drawing comes from Paul Hewitt. You know, I told you about him. He has this book, Conceptual Physics, but he was very good at drawing. First, he wanted to be an artist before going into physics, but when someone get a punch, right? He does not. What should he do? Should he stay like this, stiff, and take the punch, or should he follow through, roll over? It's called. Exactly, pull back, right? It's called rollover. Why? Because for the same change in momentum, it's going to be knocked out on the floor, maybe, right? If you increase the time, right? So you roll over, you're going to decrease the force of impact. Now, if you do that's how they do it. You know, for boxing, that they learn how to do it. They learn to roll over, right? You don't want to take the whole impact. So if you have a small force of impact, the force will be huge. That's why you have the airbag. For the same change in momentum, you're going to stop at the end if there is a crash. With the airbag, you increase the time of impact, you're going to decrease the force of impact. Does it make sense? So it's called a rollover. You want to roll over. What do you think for so this truck can be stopped by a stack of hay, or it could be stopped by a brick wall, right? And so in both cases the truck is gonna stop, right? So in which case the force will be the largest? The brick wall. Does it make sense for everyone? Because the time of impact will be small, so the force of impact will be big. Here you increase the time, you decrease the force. If you jump, do you stay with your knees stuck, or do you bend the knee? Bend, very good, because you increase the time of impact, you decrease the force, right? Otherwise, the knees are very fragile. It's very easy to hurt your knees. Okay. Let's try do number 1. You feeling better? When you feel dizzy, the trick is you take salt. But not any kind of salt. Celtic salt. Because it has magnesium, it has 60 minerals, it's the best. The salt that you buy from the supermarket, it's all synthetic. It's not good. Celtic salt. It's very cheap. You can buy it on online. It's from France, that's why. Guérande. It's called Guérande. It's from Grand Bretagne. You know, it's part part of France. So anyway, let's go back to the physics. Let's try to do number 1. You can help each other, talk to each other. Bless you. Yeah. Okay, so that's right. So force times time equals the mass times the change in velocity. So first you have a braking force of 1200. So 1200. And you apply it for 10 seconds. And you have a change in momentum because that's how much you are slowing down. And now you want to have the same change in momentum. So the change in momentum will be the same, but instead you want to apply that force over a shorter time. So that means your force has to be larger, but you want to have the same change in momentum. Okay, so that's your change in momentum. Do you understand? So if B equals A and C equals A, so B equals C, obviously. So 1200 times 10 equals F times 6. So F equals you divide by 6, so 200 times 10. Agree? Okay. Everyone? Do ask question. Let's see, number 2. Let's do number 2. And remember, you need to use a textbook. You need to study from the textbook. Okay, it doesn't hurt to make a drawing. So it was already going 2.5 meter per second. And someone is pushing. Okay, so there is a push here. 380 Newton. That's the velocity. Looks like kinematic, so it's going to increase. And now it's going, I should put the velocity here, 6.2. Okay, so do it. I'm just taking my time. It's better to do the velocity here. Okay, so it's pushing all the way. So what do we know? We know that the initial velocity is 2.5. Then we know that the final velocity is 6.2. Okay, what else do we know? We know that the applied force, the net force, is 380 Newton. We know that the time of impact or elapsed, or the time during which the force is applied, is 4 seconds. So all you have to do is apply the equation, force times time, so that will be the impulse, equals the change in momentum. So this is a vector, this is a vector. That's a change in momentum, that's called the impulse. So 380 times 4 equals mass. Final velocity, we have to be very careful with that, minus 2.5. Yeah, 411 kilograms. I could have said instead, I could have used force equals mass times acceleration. So here you have the force, which is 380, equals mass times acceleration is delta V over delta T. You get the same thing. Okay, number 3. Just to use the terminology. Okay, we are using the terminology here. Average force. So we have a force here. We have a time of impact. So by definition, the impulse is just for you to get acquainted with the new terminology. So what's an impulse? Is just force times time. What's a momentum? What's a change in momentum? Is just the mass times the change in velocity. And what does Newton say? Newton say impulse equals change in momentum. Okay, or F times T equals M delta V. Okay, so what's the magnitude of the impulse? 12, right? Because it's going to be the force times the time. So that's called J. In magnitude, we're walking along a straight line. So it's going to be 300 times 0.04, which is 12 Newton. You see, it's going to be easier when there is less trig. I don't know what's wrong with trig. It's not my fault. You have to blame the trig that you took some time long ago, if you did take it. But it's going to be easier without trig. So what is the change in the golf's momentum? Yes, it's going to be the same thing, right? Impulse equals change in momentum. If there is a force over a time t, the momentum will change. Impulse equals change in momentum. They're going to be equals to each other. So the change in momentum is, by definition, equals to the impulse. So it's going to be also 12. And here I did a mistake. It should be Newton second. Newton second. So usually you can also write Newton second, or you can say kilogram, because this is kilogram meter per second. This is the same thing as that. It's the same unit, right? Here I unpack the Newton, and then you see you're gonna get the same thing. So the momentum is, I unpack the Newton and multiply by second, you're gonna get the same thing. Okay, C. What is the force? Hmm? So what is the force? Yes. So okay, so Newton third law, right? So you have a golf, and then you have a golf ball here, and so okay, so this is exerting a force here on the golf ball. So this is we call that number 1. This is number 2. Thing number 1, thing number 2. This is 1 on 2. So because of Newton's third law, there will be a force on the club 2 on 1. They're going to be equal to each other, because you cannot hit without being hit, and you cannot hit harder than you are being hit. So the force is the same, not the consequence. The golf club is not going to, there will be a recoil, but it won't be as bad. But the golf ball, zoom, right? It has a small mass. So that's why the golf club here have a very heavy mass. I don't know, the very expensive one they made of titanium or something like this, very, very expensive. They are quite expensive, those things, if they have good quality. So that way you increase the mass, you decrease the recoil, you decrease the consequence. Does it make sense? Okay, let's see if we have another one just to make sure, because it's going to be on the test. So that way we review at the same time. Oh, no, it's good. 3:30, we have time. Okay. So again, impulse equals change in momentum. What is the impulse? Is the force times time. What is the momentum? Is the mass times the change in velocity. Okay. So you can help each other. You can talk to each other as we go along. So force times time will be, yes, very good, 7 Newton second. Is that clear for everyone? The only thing that is hard to digest, in physics at the beginning is the trig. So it's not me. So B, what is the change in momentum? Exactly, it's going to be the same thing, 7 kilogram meter per second. Change in momentum is the impulse. If you apply a force, but the time is too short, it's not going to go anywhere, right? So, for example, remember an experiment that you could do. I show you a video. So we have a string and something super heavy, like it's made of steel or something very, very heavy. You have a string here and then you have a string there. And if you pull very, very quickly, this string is going to break because the time is so small and the mass here is so large, it has so much inertia that you are not going to get the momentum to change. Do you understand? So that string is going to break. So if you have a force, but the time is so tiny because you pull very quickly, like in a very small time, the mass is so big that the change in velocity will be very small. So it's not going to move. Okay, so if you want to have a change in momentum, and especially if inertia is very large, you need time for the force to build up. So you can do that experiment. If you pull very, 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 very slowly, now you increase the time, and this string here is going to break. You always have resistance from inertia. Things don't want to change their state of motion. That's laziness. We have inertia. I need to move, but no, I don't feel like moving, right? It's very hard to move. 6. Like the best example in my classes is that students always go back to the same seat. Once the first semester, the first day, they find a seat and will come back to that seat. Right? Isn't that true? That's inertia. Because you save energy. You don't have to think, where is it I'm going to sit? What is the best seat? Mass. Okay, why don't you? It's called a meat. Okay, I forgot. It's not a glove, it's a meat. Okay, so try to do this one. So J is the impulse equals the change in momentum. That's your impulse. What's the change in momentum is the mass times the change in velocity. Change in velocity. What's the change in velocity? It's the final velocity minus the initial velocity, and it's in vectors. It's vectors here, vector there, so it could be positive or negative. Okay. So now it's traveling. So this is the initial velocity. Rest means this is 0. Okay, so what do you find? 20. 20? Oh, for 4.8. 4.8? 4.8 once, 4.8 twice. Do I have a 4.83? Mass is the mass, 0.12. Final velocity is 0. Minus initial velocity is 40, so it's going to be, yes, so 0.8 in magnitude, negative 0.8. Agree? Don't fall asleep. Huh? Yes, why did I put that? Thank you, I don't know. Thank you. That's when I start to be tired. That's negative 4.8. I have to focus. Focus for 4.8 Newton second. Agree? Okay, the change in momentum, it's going to be the same as the impulse, right? Impulse equals change in momentum, so it's going to be 4.8. And you can keep this, or you can say kilogram meter per second. Okay, because force equals ma. So Newton is kilogram times meter per second. So if you multiply Newton per second, you're going to get kilogram meter per second, because this one goes away. So these two units is the same. But usually for momentum, we like kilogram meter per second. Yeah. Agree? Okay. And by the way, you have in my Dropbox, there is, I go over. So if you have any question, let me know. Okay, let's do just number 13. So this is more, so sometimes when you have Newton second law, okay, you have two ways to do it. You can say, depending on the equation, you can say a force applied during a time t, so over a time t, okay, you don't let go, you keep pushing or pulling. It's gonna cause a change in momentum. So this is called the impulse. This is called the change in momentum. Or you can say the force equals m delta v over delta t. You see, I divide both sides by delta t. So F equals ma. It's the same thing. Except here, we can make sense of everyday phenomenon, right? We can explain a lot of things in sport, including boxing. So in boxing, there's a lot of momentum involved. So for example, if you have a cross, I don't know if you know boxing, but if you have a cross, you increase the time. Increasing the time, you increase the force. Okay, so this is super easy. So F equals ma. So you can do a force is 40 equals mass is 5 times acceleration. Okay, so you have the acceleration is 5 goes into 40 8 times. Do you agree? Now you can take this one, so it will be the same, right? You just have to divide both sides by the time. Okay, so do remember one question like this for test number 2. Don't confuse weight and mass. Weight is a force due to gravity, right? It's the Earth or a planet pulling toward its center, but the mass is inertia. So on Earth, if the weight is 600 Newton, that's a force. If you want to find the mass, you divide by 10 about. So that will be 60 kilogram, right? And 60 kilogram, how do we go from kilogram to pound? You multiply by 2. So 120 pounds, right? But or you can divide this by 5. You get also 120, about 120 pounds. But pound is a force. So it turns out in the British system, the unit for mass is the slug. So I don't know what slug. I don't know how many slugs you are made of. I don't know. But it's a slug. The unit for mass in the British system is the slug, and the unit for force is the pound. That's confusing. Okay. So if I ask you, let's say you have a bouncing ball, and both of them have the same mass. So this is 1 kilogram. This is 1 kilogram. One is bouncing off, and one's just crashes on the wall, right? It's like a tomato. You see tomato, they don't bounce off. If you throw a tomato to someone you don't like, it's gonna go, right? It doesn't bounce off, right? So the same mass. This one bouncing off. This one doesn't bounce. So can you find the impulse in each case? Impulse. So mass times the change in velocity. Can you do that? More you do here, less you have to worry about the test. Remember that. So we want to find the impulse. Impulse is change in momentum. There is an impulse, a force over time during a time t. There is a change in momentum. Impulse is what causes the change in momentum. So bouncing ball, and then we have 1 kilogram, so 2 pound tomato, and here arriving here the tomato stop. Okay, so what's going to be the impulse in this case? -6. Do you all agree with that? Okay, remember, plus, minus. So it's going to be the mass. The change in velocity, final velocity is -3, minus initial. So that's going to be -6 Newton second. Agree? So J here will be 1 kilogram. What's the final velocity? 0. Tomato, chung. Right, so it's going to be 0 minus initial, so that's going to be -3. Conclusion. Something bounce off, it's going to hurt more than just something that will stop. Right? So there is like in karate, for example, if you want to make sure to bounce off, right? And you're going to hurt more than you just go like this. So when it's bouncing off, it's going to cause more change in momentum. There will be a larger impulse when it's bouncing off. You can do a demo, like someone can sit on a chair, a rolling chair, right? And someone send that person on the rolling chair to you. You're gonna feel it's gonna be harder to stop and to throw back than just to stop it. It takes always more force to make something bounce than something stop. So in that case, it takes, for the same time, it takes twice the force. In this case, twice the force, half the force. Impulse, it's what causes change in momentum. Agree? See that? So I think you can imagine all kind of demo. So there is a demo called the happy and the sad. Happy and sad. I don't know if I can find the happy and sad ball.
In this demonstration, I have two balls that look the same, but one is happy and one is sad. I have two balls that look the same, but one is happy and one is sad.
First, I'm going to hang the sad ball from this string, bring it back, and release it so it hits the block.
So
The
this
question
one
is,
does not
what will
bounce.
happen to the block when the ball hits it? Will it stay upright, or will it fall over?
So the sad ball doesn't bounce off, right? No.
The blocks stay upright. This is because when the ball hit the block, it was roughly an inelastic collision. The ball and the block
So it doesn't
became one
bounce,
mass,
smaller
essentially,
force.
with the momentum, the original momentum of the ball, which was not enough to knock over the block.
So
Now let's
we're
repeat
gonna have
the
a
experiment
bouncing ball.
with the happy ball. What will happen when the ball hits the block? Will the block knock over, or will it stay upright?
Isn't that cool? So bouncing, more force, right? Okay. So during the gold rush, there is this guy, Pelton, who did that. It was a new. So to dig the gold, right? So you need a mill, right? So you need a wheel, and the mill here was working with water. And before his invention, the wheel here had flat paddle, so it didn't spin very fast. And then he said, "Oh, I remember physics 2053. If I make the water bounce off, I'm going to provide more impulse, twice as much, and the wheel is going to spin twice as fast." Okay, so if something is bouncing off, it will provide more impulse, so you're going to get more change in momentum. And he made money like this because it was 1870 and he had a patent, right? So it's a patented, so it was a revolution at the time during the gold rush. So you know what they say during the gold rush, you have to sell shovels, right? Don't dig for the gold. You're not going to make money with that. You sell the shovels. So it's a very famous saying, because those people who made the money at the time, they are not the one who were mining. The first one maybe, because the first one got the gold easy, but the other one, it was super hard, and then they would spend their money in bars, and they had to buy shovels, right? So they were not making money. The one who made the money is the one who sold the shovels, right, and everything around, and the bank, Wells Fargo, for example. Wells Fargo, that was at the time when they opened for the first time, because the miners, they needed a bank to put their money in. And then you have the transportations, right? Transportation to transport the gold. You see that in the cowboy movies. What else? You have, Stanford University. And he started like this, selling shovels, and that's how he became very rich. Levi-Strauss, Levi-Strauss, the jeans, that's how they made their money, because they came up with those pants that the miners loved because it was very hard to damage, and they sold the pants, they sold the jeans, came up with the jeans, and Levi-Strauss became very rich. So that's how the first money in California was made by selling shovels, right? Not digging for gold. So what they say is, when there is an economic boom, don't chase the economic boom. You have to support the economic boom. So when people go crazy with the crypto money, for example, crypto, digging for crypto, who makes the money? The one who gonna sell the graphic cards and the computers and the hardware and the gamers, right? The gamer computers. It's not the one who dig for money. Like maybe one or two are gonna make money, but that's it. You see the point? In 2008, there was this craziness about solar energy, right? So all those startups, they all went down. They all bankrupt. They all went bankrupt. The one who made the money is the one who built the hardwares to build the solar cells. So don't chase the economic boom. You have to support the economic boom, right? So that's the lesson. So those who were making money, they are the one who support the miners, and the miners didn't make any money. That's my tangent for today. I always have some tangent I can go along, but again, if there is a change in momentum, that because you hit, for example, in that case, you're gonna hit the surface is gonna hit back. If it's bouncing off, the impulse will be huge. Because so, for example, if you want to break a brake, don't do it for demo. I don't want you to be injured because of that. If you bounce off, okay, you're going to provide a huge impulse, but the time of impact is not large enough to hurt yourself. You can bounce off, right? Like if you do boxing, there is something called the jab, and the jab you bounce off, right? You don't want to go into it. So great impulse, but small time, so you don't have time to injure yourself. So why do you think, is it open? Not yet? At what time does it open? Huh? 3 something? 3:30? 27. Okay, so larger is the time, larger is the change in momentum. So I don't know if you've seen the old movie, like 17th century. They used to have rifle, but like crazy long rifle. You see those crazy long rifle at the time of the um, American independence war, right? At the beginning with the British and the French all fighting with each other. They had this very long rifle. Why is that? Because you just have a powder here, so it was not efficient like today. So the idea is that you want to apply a force. So the force was not large, but the time was large. So by increasing the size here, you increase the time during which the force is applied, so you can have a larger momentum. Same way before all the technology that we have, the cannon had a very long nozzle, because that way they increase the time during which the force is applied, you increase the momentum. As soon as you stop pushing or pulling, then it will keep moving at a constant speed along a straight line. So you need to apply a force over a time to get a change in momentum. Which one will get the largest momentum? A baseball that you catch, or a baseball that you catch and throw back? Right? Because it's like it's bouncing. So that will provide the largest momentum. Okay. Okay, so we almost finished, right? And then it's easy. I tell you, it's gonna be easier because there won't be any trick. So don't blame the physics, it's the trick. So you can always review your trick and all will be fine.
We're trying to work that CG stuff. I thought that would be I thought that was it. Unless I just missed, unless I just need the signs. What is it? You got honor of English, you trying to express. And all equal to each other. Yeah, team one will equal team two.
Do you feel better?
Or like if you had number T1, you T2, two.
Yeah. Yeah, no, it's
Okay. Yeah, you're right. That made me think about what we